Okay, so welcome everybody. My name is Lukas. I'm from the Oracle Labs GraalVM team, and this is my colleague Radek from the Oracle Netsuite team. We're happy that you found your way into this room despite the long title of this talk. So we'd like to tell you a bit about some work we did in collaboration between Oracle Labs, the GraalVM team, and Netsuite. We're going to go out on a limb here and assume that everybody's familiar a bit with Python syntax, maybe knows a bit about GPUs, vaguely what they do. We're also going to do this in a somewhat reversed order, so we're going to present the solution first, and then the problem and how we solved it. We have a lot of ground to cover, and this way the kind of narrative of this talk works much better. The obligatory disclaimer: this is insight into current research, and you should take that quite literally, especially on the GraalVM side. Some of this is very much work in progress, so we're showing you what's possible now and what will be possible soon. I assume most of you have heard about GraalVM. Nevertheless, I want to give a very quick intro so that we're on the same page, and maybe there's an aspect or two that you haven't heard before. What is GraalVM? It's a very simple question with a surprisingly complicated answer. So it aspires to be ubiquitous across the cloud stack, and it runs your programs more efficiently, and it makes developers more productive. It's kind of the overall vision. And in more concrete terms, we want to provide high peak performance for abstractions in all languages. There was a talk yesterday by Thomas Wörting on this, how GraalVM removes abstractions. We want to provide a low footprint ahead of time compiled mode. Oleg Shelayev talked about this in his talks on native image. And I want to tell you a bit about the third and fourth point here, the language interoperability and polyglot tooling, and also how you can embed this into your Java applications and other kinds of applications. GraalVM at its core, it's a JDK, it's a Java runtime, so it can run all your Java-based languages like Java, like Kotlin, Scala, and so on. And it's actually very good at running these. Very good performance. It's also a runtime for many other languages like R, like Ruby, JavaScript. You can also run your native languages as LLVM bitcode on GraalVM. And then, as an important additional aspect, it cares about embedding into various scenarios, so into your Java applications, into Node, into Oracle databases, and also into native applications. And the main aspect here is that you can compile your Java applications into native images using the native image tool. For the embedding side, I want to show just one example here as an introduction. So here I'm creating a new polyglot context, as we call it, and I'm using it to run a piece of R code. R is a statistical programming language. It has good support for drawing charts and so on. So I'm using a piece of code with the lattice package here to draw a histogram and turn it into an SVG string, like into an SVG graphic. And it's as simple as that. I'm getting this function out of R. It's a polyglot value in Java, and I can just execute it afterwards, give it a Java array, and it's going to do the histogram on that and give me back this lovely chart. And there's some really awesome packages in R to do that. This is just a short introduction. There's so many things that this can do with debugging and tooling and resource management and everything. But I want to bridge this whole thing over to Python. You know what Python is. It started as a scripting language. That's also why its default implementation is interpreted. It's still used a lot for system scripting, all these kind of tasks, and it's emerged as one of the most important data science languages because of its rich ecosystem. It has some very popular modules, C extensions like NumPy, SciPy, and all of those. You've heard the names. The interesting thing about Python is that it's very complex under the hood. The language runtime is extremely intricate, but it's very well designed at the surface. It's easy to learn. It's consistent at the language surface that you usually use. So you want to use Python, you want to use it in your application, so you're embedding it in your applications. And there's a whole chapter in the Python manual on how to do that, on how to enrich your C, C++ applications by embedding Python. I'm sure you've spotted the problem here. It's the C, C++ part. So if you have like your big server application written in C, C++, then embedding Python is probably not your biggest problem these days. So I assume that a lot of people will actually want to embed it in their Java code. So that's for CPython. There are other implementations of Python. For example, PyPy. It's a very good implementation of the Python language. It runs Python code very efficiently, but it's even less embeddable than CPython. There are implementations like Json and IronPython that are built on the Java and .NET ecosystems. So they are easy to use from Java, but they only support Python 2, which is going out of support soon. And these projects are also barely maintained. So it's actually hard to get approval in a company like Oracle for some of these days. And they don't support native modules. So you will not run your NumPy, SciPy code on these Python engines. So that's the gap we want to bridge. We want to have a runtime for Python that's going to run your modules and at the same time is very easy to integrate into your ecosystem. So we run with GraalVM, we run Python code very fast. The Python code itself, native code is a different question. Polyglot embedding is very easy, very consistent, works not only for Python, for many different languages, and there is even a way to execute your Python modules inside the Java environment. So not running them with any connection to native code, which can be very important in some circumstances. Our performance on Python code is comparable to PyPy. Don't want to go into too much details, but we're at the top of the flock here. I want to talk a bit about embedding your machine learning data science code using Graal Python. And for that, I'm going to use NumPy as an example. It's kind of a building block for many of these libraries anyway, and I just want to use it as an example module here. So again, I'm creating my polyglot context, and I'm configuring the Python path so that it can find the modules. Usually, in Python, you create a virtual environment, and then you have all your installed modules in there. So you can just point your context at these. And what I'm doing here is I'm using the NumPy and math modules inside an anonymous function, this lambda here, to create the geometric mean of some input. And again, I get this function, this anonymous function, just as a polyglot value. And below, I'm creating some Java array, and I'm using this geomean function without any problem. I'm telling it, give me the result as a double, because it could be anything from the point of view of Java here. And it's going to do everything in its power to create it, to convert it to a double and return it to me. And this also works very naturally for the most important data type in NumPy, the array class. So here, I'm just getting the array class, like the array constructor, from the Python environment. And again, I have it as a polyglot value in Java, and I can just execute it. And by that, I'm creating a NumPy array. And then I can use the members of this NumPy array class, like the cumulative product here. That is going to return me another NumPy array. I can print it. It's yeah, it uses the Python-specific syntax. But this NumPy array, it behaves like an array in Python, which means it will behave like an array in any language, including here on the Java embedding side. So I can query its size, I can get its elements. All of that is just going to work. And this doesn't only work for NumPy arrays, it works for any array-like data structure in any language that is supported on GraalVM. This also works for multidimensional arrays. I'm doing a two-dimensional matrix here using the same constructor function because NumPy arrays are n-dimensional. So yeah, again, the same thing. When I'm going to access it, I'm going to select the row first and then the column. What makes NumPy arrays so interesting is that they implement a lot of functionality, a lot of operations on them. For example, you can add a scalar value to a matrix, and then it's going to add this value to every element of the matrix. I can do this in several ways. The first one here is by calling the magic function in Python. The array class has a member that's called __ add. So I can just call that, give it the scalar, and it's going to do the addition. Of course, this requires some knowledge about the internals of Python. So what I can also do is just write a piece of Python code. Again, I'm using an anonymous function here and just write the addition. And the fact that this piece of code is marked as being Python code makes sure that the plus operation is handled in the Python-specific way. So then I get this plus function, and I can just use it again and give it the matrix and 1, and I get the same result here. So it's important to know that this piece of Python code, the lambda, it's not like a plus in Java, like an integer addition or double addition. It is in Python semantics. Once your Python code is big enough, you probably want to put it into a separate file, not have it in a string somewhere. That's not very sustainable. So I created my alternating least square model class here, just has a few members. And then in this Python file, as a last statement, I'm returning this class. This is my entry point, kind of. I'm loading this file, and what I get back is this class. I can even ask, hey, are you instantiable? Can you be instantiated? Are you a class? And it says yes. And I can then use this to create an instance of this class. You see here that I'm using the same thing, a class, as a function and as a class where I create instances. That is kind of specific to Python because in Python you can use, like the way you create an instance of a class is just a function call into the class itself. Yeah, again, I'm calling a member of my own class here, the infer, and I give it a Java data structure, and it's going to return me the length of this Java array in the end. So after a while, you're probably going to settle on a specific API, and you want to make this more formal also on the Java side. What you can do is you define a Java interface, like this inference interface here, and then you can say, well, I have this instance of my ALS model class, and I know that it implements everything in this interface, so I can just get me an instance as this interface on the Java side, and then the call is simpler and more Java-like. I can just call into the interface function, but it's going to do the same thing behind the scenes. Going one step further, you're going to probably turn your code not only into a Python file, but into a Python module. And then you can do pretty much the same thing you did with the class, with the module. I'm using the NumPy module as an example here, but you can fill in your own module. So I'm using a piece of Python snippet to get me the module class, the module itself, the NumPy module. And then I can also, again, call functions on it. I could also define myself an interface for the members of the module itself. What I'm doing here is I'm creating a NumPy array with a two-dimensional matrix, and int values in it. Of course, I can ask NumPy afterwards about the data type of this. I don't want to go into detail on this much more. It works for many packages, many Python modules that you will want to use. I mentioned this managed mode execution before. So the interesting part in Graal's Python runtime is that it runs native modules not as native code, but as bitcode. So we compile all the C code in the modules into bitcode, LLVM bitcode, and run that using GraalVM's LLVM bitcode runtime. And this bitcode runtime has a special mode called managed mode, which cuts all links to the native world and executes it completely inside the Java environment. So you will not have calls to actual native functions, to native syscalls. You can define your own view of the file system. This is a very good way to manage your Python code in a trust-aware environment. And the other thing is that we found actual bugs in the Python, in CPython, in the native API of CPython, because the error detection in this LLVM interpreter is sometimes better than the one in the normal LLVM compiled code. The Graal Python runtime is obviously work in progress. A lot of things work at the moment already. You're not going to install your arbitrary package using pip, because pip doesn't work at the moment. It uses so much of the Python API that it doesn't work yet. But we ship our own installer called ginstall. It's going to install you NumPy and pandas and SciPy and whatever in versions that we know work best. So pandas, NumPy, they work for a wide range of things in the latest builds. The performance of the code inside the native modules has a significant startup overhead. We're working on that. Also, SciPy started working very recently. It's work in progress. Try your code, but it may or may not work. Modules with pure Python code, they tend to work most of the time. We are improving compatibility there every day. So when we're talking about embedding Python code, I mentioned JSON before, we also want to make it easy to move from JSON to GraalVM. So we provide a special JSON compatibility mode for the Python side of things. So that is going to allow the JSON-like direct imports of Java classes. It's going to have the same exception handling. So it makes it quite seamless. It does not replace the Java side of things, because people usually use the JSON interpreter classes directly, and those would be very hard to re-implement for us. So the Java side of things needs to be changed to use the GraalVM embedding API. But I mean, we have people already who want to use this as a JSON replacement, and we're always eager to hear about more use cases for that. So if you want to give it a try, you can just download it. Google will lead the way for you. When you download GraalVM, it doesn't include all the languages immediately, but it's easy to install them. There's a Graal updater binary that does all the installation for you. Just install it. Then it's the easiest way to do this, not pollute your local Python environment, is to just use a virtual environment. So I'm creating a virtual environment here using the Graal Python executable. We named it Graal Python because it's not 100% compatible yet. So if we name it Python, it's going to mess with your Python scripts. We didn't want that. So it's called Graal Python. And then if you activate your local environment, you can install packages like NumPy, and then, well, just start using them from Python, like from the Python REPL, or also from your Java code. So I hope you will give this a try. And one other project that we've been working on in collaboration with NVIDIA is the CUDA connector for GraalVM. I'm not going to talk much about the basic GPU programming model. I'm probably not the most qualified person for that anyway. But if you've never tried writing something for GPUs, you should give it a try. It's quite amazing to see your code process data at rates of a terabyte a second. This is really crazy. But as with many other things, the problem is that every language has different bindings for your GPU libraries. And it's the same for CUDA. So for most of the popular languages, you actually have several different bindings for CUDA with different sets of supported features, different approaches. The main thing these bindings need to solve is this translation between your managed environment, like in Python or Java, and the unmanaged CUDA C++ environment. And that's what GraalCUDA is trying to solve. Its goal is to have efficient exchange of data between your host language, like Python or Java or any of the other languages on GraalVM, and the GPU without burdening the programmers. So it will expose the GPU resources, for example, memory or compute, in ways that are native to the language that you're using. If you have some memory mapped on the GPU that contains an array, then this should look like an array in whatever language you're using. In order to execute GPU kernels, either existing kernels, or you can also define your own GPU kernels on the fly. GraalCUDA has support for that as well. And the interesting part is that it's one set of bindings for CUDA that works for all languages on GraalVM. And they work the same in all languages. And the way this is done is by implementing GraalCUDA as a Truffle language, which is not 100% correct because CUDA is not a language, but it allows it to work with all the other languages very efficiently. It's developed mainly by NVIDIA in collaboration with Oracle Labs under a BSD license. And I just want to show some code here. So the main point is this device array class that we're using here to create an array, single or multi-dimensional array, in a memory region that's visible both on the CPU and the GPU. So I'm creating two here. One of them has 1,000 integer elements and the other 100,000 float elements. And these device arrays, they work like arrays in every language. I'm using Python code here, but it's the same for all the others. And interestingly, those data structures run as fast or faster than the language's own data structures, because they are implemented efficiently and they also don't have some of the special semantics that the languages have. For example, R has special handling for NA values. We don't need to do that in those device arrays. And then you have your GPU kernel. GPU kernels are written under the assumption that your kernel is not running in one single straight line, but that it's running as a number of threads in a number of blocks. And you can configure that, and every kernel execution thread knows which thread it is in which block, and the algorithms are then written based on this information. And the connectivity is different between threads inside the same block and different blocks, of course. So yeah, this is a more concrete example where I'm creating some device arrays for input and output data, and then I have my kernel from the last slide, and I'm just going to build the actual kernel using the build kernel function, give it the parameter types, and then configure the kernel with 160 blocks and 256 threads per block. And afterwards, I can just access the output array like any other array that there is in my Python code or JavaScript code as it is here. And I think this is really the simplest way to access GPUs that I've seen so far. GR CUDA does a lot more than that. It includes some existing GPU accelerated libraries for you to use. You can pre-compile your kernels to get rid of the small startup overhead there. Lots of other functionality. And there's lots of interesting features planned. You can just go to the GitHub page. There's issues for the interesting features there. And there was also a blog post by René Müller recently. He's the main developer of GR CUDA on the NVIDIA side. So he describes everything and in much more detail on the NVIDIA blog. And yeah, that's what I want to tell you from the GraalVM side of things. And Radek is going to tell you about the NetSuite side of things.
Thanks. Hi, I'm Radek. I work at Oracle NetSuite. And I would like to tell you a story about how we use what Lukas has been talking about here, and how it helped us to deliver our POC for our machine learning POC for recommender system. So for a little context, I'll try to be fast. What is NetSuite? It's a big suite of modules: ERP, CRM, HCM. We are number one cloud ERP on the market. We have data centers all over the globe. What is really important to mention here that the primary technologies that NetSuite is based on is Java and Oracle DB. A part of the suite is commerce solution. So the flagship is SuiteCommerce. I work. I'm a part of a commerce team in Brno, Czech Republic. We support B2B, B2C. It's an omnichannel solution. Point of sale. This is very convenient for our customers because there's no integration needed. It's kind of works out of the box with the rest of the suite. This January, we started working on a proof of concept for next generation recommender systems for our e-commerce solution. There are a couple of use cases we are supporting. One of them is this general recommendations widget. You log in, gives you recommendations. It's pretty standard. You see it in Amazon, Netflix, YouTube, everywhere. The other use case for this proof of concept is something we call search boosting or merchandising. We use the recommendation data to reorder your search result on e-commerce. When doing a lot of research last winter, I stumbled upon this quote, and it's my favorite ever since. And this is the reason why we wanted to deliver some of it's a famous algorithm called matrix factorization. It's kind of an evergreen in the field of recommender systems. Who here has heard of matrix factorization? Raise your hand. There's one person, perfect, or two. Good. That relieves some pressure of me. It belongs in the collaborative filtering family, which basically means it does not use content data for our items or users. It uses interactions between items and users instead. This particular flavor that we are using uses implicit feedback, which is as opposed to explicit ratings, star ratings on your IMDb site or something like that. That's not what we use. We use implicit feedback like clicks and transactions. If you look at the picture here, the D matrix is an input. the W and T, that's the computed model. That's what we try to achieve. We want to compute W and T in a way that if we multiply those two matrices, we got D back. It sort of compresses the original matrix, which gets us generalized information about. We try to represent our items and users in a small space, which generalizes the taste or features. Once this is computed, it's very easy to retrieve either prediction for item user pair or for two items, kind of what gets bought together. So after this research, after the decision that we would work with matrix vectorization, we started prototyping, and we tried a lot of things. There were two libraries out there that we particularly liked. One's called Implicit by Ben Fredrickson, and the other one is called LLVM by Maciej Kula. I hope I said it right. Now, those are great. They are blazing fast, which is what you need when you try to develop your model. They work really well. The Implicit uses alternating least squares for optimization, while LLVM uses stochastic gradient descent. The problem with those two libraries, we thought, is they are written in Python. And I mentioned before that we're in Java. We're in Java business, and we found ourselves in a bit of a gap between our huge monolith Java application and our nice Python prototypes. Well, at first we bridged that gap by implementing what we wanted in Java, but then we got in touch with Lukas's team, and we tried to work on an embedded Python implementation that we call straight from our Java application. And we started working on NVIDIA CUDA implementation using GraalVM CUDA. And we integrate all this in our Java application using a model algorithm interface. That's how we call it. The model algorithm interface is a simple interface that it prescribes you how to train a model and where you store your predictions. So, switching some cables now to give you a really good idea of what we have done. And if demo fails, there's always a video. Let me just try this real quick. Okay, the fallback it is then. So in NetSuite we have something we call admin tools. These are documents that are not customer facing. This is for us developers and NetSuite employees to access some settings on our customer accounts. We have our tool for managing recommender system models. It starts by putting in account ID and a site ID. We do recommendations in a site scope, or scope of a site. There can be multiple models implemented using the model algorithm interface, as we have it right here. They can be managed from here. We have something we call model definition that prescribes how a model is going to be trained. Once a model is trained, it creates something we call model instance. That's a ready to be served model. It computes and stores predictions for individual users. It's really simple to manage. This is creating a new model definition. The interesting part here is that I can choose from all the implemented algorithms. I really hope when shooting this video I clicked that. Oh, I didn't. So I can choose. I can now choose from Java matrix vectorization implementation, from GR CUDA implementation, and from Python implementation. Once the model is trained, we can have a look how it looks like on the site. We have imported a public data set to a test account. It's called online retail. It's kind of home, improvement, accessories. Is this still running? I'll move it on a little bit. So this is our development. That's how a development site looks like. And on the homepage, I get my recommendations. We didn't have images for this data set, so we just put random kitties and dogs everywhere. One last thing this admin doc tool can do is to create A/B tests where we can pitch different models against one another. The only real way how to evaluate recommender system is by doing an A/B test. We are able to pitch one model against one another, so we can compare how GR CUDA model works against our baseline implementation in Java. Yeah. So, sorry about not being able to provide a live demo. Switching cables once again. Right back. Awesome. So what do we did to make this all happen? First, we acquired something we call Netsuite Lab environment, which basically mimics a Netsuite data center. We deployed it on a combination of multiple OCI shapes. OCI stands for Oracle Cloud Infrastructure. We used combination of bare metal machines and virtual machines. One of them has GPUs, which is handy. We installed GraalVM, CUDA, Graal Python, and GR CUDA in that environment. All those terms Lukas has mentioned before. And we installed NetSuite, but we did not deploy it on normal JVM as we do. We ran it on GraalVM, and it was a very seamless transition. Now, I'll talk a little bit more about what we got out of it. So, we bridged the gap. With the Python model, we can now embed whatever Python code we find online, whatever nice open source libraries. and it's easy to do. Now, if you put a little more work in it and create CUDA implementation of your model, you get huge performance boost. On this chart, it's really comparing apples and oranges because we're comparing CPU performance versus GPU performance. But it is comparable in a sense. You can go to your favorite cloud infrastructure provider and see how much is a GPU hour and how much is a CPU hour. And I did this with OCI. Please don't quote me on this, but it seemed to me like the CUDA model computation could be about 5 times cheaper than when we do it in CPU. Yeah, so that's all I wanted to talk about. Lucas, do you have something to close with?
No, I mean, yes, we are very happy with the way this turned out with NetSuite. Glad to see it used in like a big stack. We found lots of issues that we wouldn't have found otherwise, like configuration on specific versions of your Linux environment, where some operating system features are available or not available, things like that. So this was a very interesting experience for us. And yeah, we're hoping that you give GraalVM and its Python runtime a try as well. Maybe also the CUDA runtime, and let us know how it worked for you. And I think with that, we have more than enough time for questions.
Any questions at all?
Yeah.
I know that Oracle has machine learning, but it's in the database, isn't it? But you probably chose to use Python because there are a lot more libraries.
Yes. So the machine learning data science field is, of course, something that's being worked on from many angles, also inside Oracle. Yeah. There is support, for example, for R in the database. And yeah, you're right. We chose this approach because we wanted to use the latest and most convenient Python modules.
This is all proof of concept. So we are always exploring new ways how to do things, and this seems like a very good way. This one, and we are working on multiple things at the same time, obviously. Any more questions?
That was a very good question. You want some socks?
Thank you very much.
Go ahead, please.
Give me a step-by-step example before. You ended up putting the Python code in a separate file and loaded it at runtime, which turned it then into bytecode, sort of, yeah?
There's no bytecode involved, but yeah.
My point is this step, when of course there's an error in Python, you get a runtime exception. Would it be feasible and possible to do this step at compile and build time, like when you compile your Java files, compile your Python file as well?
Do you want to repeat the question?
Yes. So I'm sure you've heard of the native image tool that can turn a Java application into a native binary by ahead of time compiling it. And what you can do there with languages like Python is to initialize part of your environment, like preload some modules, and have them included in your boot heap. Like when you then start the binary that is the result of this ahead of time compilation, it will have those modules ready to go. And since you're parsing them during the build process of this module, you will get also errors at that point. But whether you can use native image in your specific environment depends on various factors. But that's one way to do it. Yeah. You also want some socks?
Thanks.
Are there any more questions for Lukas or myself?
If not, then thanks again for listening to us.